Field theory is the branch of mathematics in which fields are studied. This is a glossary of some terms of the subject. For the unrelated field theories in physics, definition of a field. A field is a commutative ring in which 0, 1 and every non-zero element has a multiplicative inverse. In a field we thus can perform the operations addition, subtraction, multiplication, and division. The non-zero elements of a field F form an abelian group under multiplication. This group is typically denoted by F times the ring of polynomials in the variable x with coefficients in F is denoted by F x. Basic definitions. Characteristic. The characteristic of the field F is the smallest positive integer n such that n1 equals 0. Here n1 stands for n summans 1 plus 1 plus 1 plus 1. If no such n exists, we say the characteristic is 0. Every non-zero characteristic is a prime number. For example, the rational numbers, the real numbers and the p-adic numbers have characteristic 0, while the finite field ZP has characteristic p. Subfield. A subfield of a field F is a subset of F which is closed under the field operation plus an asterisk of F and which with these operations forms itself a field. Prime field. The prime field of the field F is the unique smallest subfield of F. Extension field. If F is a subfield of E, then E is an extension field of F. We then also say that E, F is a field extension. Degree of an extension. Given an extension E, F, the field E can be considered as a vector space over the field F, and the dimension of this vector space is the degree of the extension, denoted by E, F. Finite extension. A finite extension is a field extension whose degree is finite. Algebraic extension. If an element alpha of an extension field E over F is the root of a non-zero polynomial in F x, then alpha is algebraic over F. If every element of E is algebraic over F, then E, F is an algebraic extension. Generating set. Given the field extension E, F and a subset S of E, we write F for the smallest subfield of E that contains both F and S. It consists of all the elements of E that can be obtained by repeatedly using the operations plus, minus, asterisk, on the elements of F and S. If E equals F, we say that E is generated by S over F. Primitive element. An element alpha of an extension field E over a field F is called a primitive element if E equals F, the smallest extension field containing alpha. Such an extension is called a simple extension. Splitting field. A field extension generated by the complete factorization of a polynomial. Normal extension. A field extension generated by the complete factorization of a set of polynomials. Separable extension. An extension generated by roots of separable polynomials. Perfect field. A field such that every finite extension is separable. All fields of characteristic 0, and all finite fields, are perfect. Imperfect degree. Let F be a field of characteristic p greater than 0, then A is a subfield. The degree F is called the imperfect degree of F. The field F is perfect if and only if its imperfect degree is 1. For example, if F is a function field of n variables over a finite field of characteristic p greater than 0, then its imperfect degree is Pn. Algebraically closed field. A field F is algebraically closed if every polynomial in F x has a root in F. Equivalently, every polynomial in F x is a product of linear factors. Algebraic closure. An algebraic closure of a field F is an algebraic extension of F which is algebraically closed. Every field has an algebraic closure, and it is unique up to an isomorphism that fixes F. Transcendental. Those elements of an extension field of F that are not algebraic over F are transcendental over F. Algebraically independent elements. Elements of an extension field of F are algebraically independent over F if they don't satisfy any non-zero polynomial equation with coefficients in F. transcendence degree, the number of algebraically independent transcendental elements in a field extension. It is used to define the dimension of an algebraic variety. Homomorphisms. Field homomorphism. A field homomorphism between two fields E and F is a function f such that f equals f plus f and f equals ff for all x, y and E, as well as f equals 1. These properties imply that f equals 0, f equals f minus 1 for x in E with x 0, and that f is injective. Fields, together with these homomorphisms, form a category. Two fields E and F are called isomorphic if there exists a bijective homomorphism f, E, F. The two fields are then identical for all practical purposes, however, not necessarily in a unique way. See, for example, complex conjugation. Types of fields. Finite field. A field with finitely many elements. Ordered field. A field with a total order compatible with its operations. Rational numbers. Real numbers. Complex numbers. Number field. Finite extension of the field of rational numbers. Algebraic numbers. The field of algebraic numbers is the smallest algebraically closed extension of the field of rational numbers. Their detailed properties are studied in algebraic number theory. Quadratic field. A degree 2 extension of the rational numbers. Cyclotomic field. An extension of the rational numbers generated by a root of unity. Totally real field. A number field generated by a root of a polynomial, having all its roots real numbers. Formally real field. Real closed field. Global field. A number field or a function field of one variable over a finite field. Local field. A completion of some global field. Complete field. A field complete W, R, T, to some valuation. Pseudo-algebraically closed field. A field in which every variety has a rational point. Henselian field. A field satisfying Hensel lemma W, R, T, some valuation. A generalization of complete fields. Hilbertian field. A field satisfying Hilbert's irreducibility theorem. Formally, one for which the projective line is not thin in the sense of Serre. Kroneckerian field. A totally real algebraic number field or a totally imaginary quadratic extension of a totally real field. CM field or J field. An algebraic number field which is a totally imaginary quadratic extension of a totally real field. Linked field. A field over which no biquaternion algebra is a division algebra. Frobenius field. A pseudo-algebraically closed field whose absolute Galois group has the embedding property. Field extensions. Let E, F be a field extension. Algebraic extension. An extension in which every element of E is algebraic over F. Simple extension. An extension which is generated by a single element, called a primitive element, or generating element. The primitive element theorem classifies such extensions. Normal extension. An extension that splits a family of polynomials. Every root of the minimal polynomial of an element of E over F is also an E. Separable extension. An algebraic extension in which the minimal polynomial of every element of E over F is a separable polynomial, that is, has distinct roots. Galois extension. A normal, separable field extension. Primary extension. An extension E, F such that the algebraic closure of F and E is purely inseparable over F. Equivalently, E is linearly disjoint from the separable closure of F. Purely transcendental extension. An extension E, F in which every element of E not in F is transcendental over F. Regular extension. An extension E, F such that E is separable over F and F is algebraically closed in E. Simple radical extension. A simple extension E, F generated by a single element alpha satisfying for an element B of F. In characteristic P, we also take an extension by a root of an Artin-Schreier polynomial to be a simple radical extension. Radical extension 8 where each extension is a simple radical extension. Self-regular extension. An extension E, F such that E phi is an integral domain. totally transcendental extension in extension E, F such that F is algebraically closed in F. Distinguished class A class C of field extensions with the three properties: if E is a C extension of F and F is a C extension of K, then E is a C extension of K. If E and F are C extensions of K in a common overfield M, then the compositum F is a C extension of K. If E is a C extension of F and E greater than K greater than F, then E is a C extension of K. Gallows theory. Gallows extension, a normal, separable field extension. Gallows group, the automorphism group of a Gallows extension. When it is a finite extension, this is a finite group of order equal to the degree of the extension. Gallows groups for infinite extensions are profinite groups. Comma theory. The Gallows theory of taking nth roots, given enough roots of unity. It includes the general theory of quadratic extensions. Arton-Schreier theory covers an exceptional case of comma theory, in characteristic P. Normal basis, a basis in a vector space sense of L over K, on which the Gallows group of L over K acts transitively. Tensor product of fields, a different foundational piece of algebra, including the compositum operation. Extensions of Gallows theory. Inverse problem of Gallows theory. Given a group G, find an extension of the rational number or other field with G as Gallows group. Differential Gallows theory, the subject in which symmetry groups of differential equations are studied along the lines traditional in Gallows theory. This is actually an old idea, and one of the motivations when Sophus Lie founded the theory of Lie groups. It has not, probably, reached definitive form. Grothendieck's Gallows theory, a very abstract approach from algebraic geometry, introduced to study the analog of the fundamental group.